Welcome students to this session on operations research. In this session, we will be discussing about 2 into 2 games without saddle point using arithmetic method, or it's also called as the analytical method. In the previous session, we discussed about problems with saddle point, that is maximum value was equal to minimax value, and the corresponding strategies at this equilibrium point or the saddle point were the optimal strategies of player A and player B respectively, and the value of the game was established from that particular point. The value at that particular saddle point was the value of the game. But what happens if there is no saddle point in a problem? Maximum value is not equal to minimax value. So in that case, it is a mixed strategy problem, that is, it's a probabilistic method of finding out the optimal strategy. So there will be some probabilities involved here in the evaluation. And also in this particular session we will be discussing about 2 into 2 games, that is 2 strategies of player A and 2 strategies of player B. Games where both players A and B have 2 strategies each. So that's why it's called a 2 into 2 game. Player A will have 2 strategies and player B will have 2 strategies. And if there is no saddle point, that is maximum is not equal to minimax, then how do we arrive at the optimal strategies? Let us take a problem now. In this particular problem, player A has 2 strategies A1 and A2. Player B has 2 strategies B1 and B2. So it's a 2 into 2 matrix because player A has 2 strategies and player B also has 2 strategies. So it's a 2 into 2 problem. The payoff matrix is given and the payoffs are given, that is the payoff values are given 1, 7, 6, 2. Solve the above game using the arithmetic method or the, and these are the payoffs. A1, a payoff of 1 here means a gain of 1 to A, whereas it's a loss of 1 to B. Similarly, a value of 6 here, gain of 6 to A and a loss of 6 to B, and so on. So all these things have been understood from the previous sessions. So here we have to now solve this particular problem by using the analytical method or the arithmetic method. So now you don't know whether this particular problem has a saddle point or not. You have to first check whether this particular problem has a saddle point or not. So let us first check whether this particular problem has a saddle point or not. First we will find out the row minima here. The row minima 1 and 7, between 1 and 7, 1 is the minimum. Similarly between 6 and 2, 2 is the minimum. Similarly, if I see the column maxima now, the maximum in this particular column is 6 and the maximum here is 7. So now you have to find the maximum value and the minimax value. So from here I can find out that the maximum of this minimum is 2. The maximum of this minimum is 2 here. You can see here this is the maximum. So this becomes the maximum value. So maximum value here is 2 and the minimum of this maximum is this 6. As you can see here, 2 is not equal to 6. So maximum is not equal to minimax. Maximum is not equal to minimax, hence saddle point does not exist. So in any game theory problem, the first step that you have to do is, after you establish the or formulate the payoff matrix or draw the payoff matrix and enter all the payoff values with the strategies, first you have to find out whether there is a saddle point or not by finding out the row minima and the column maxima. Then find the maximum amongst the row minima and the minimum amongst the column maxima. So maximin and minimax values are arrived at. So then compare this maximin and minimax values, and if they are equal, then we can say saddle point exists, and directly you can find out the optimal strategies corresponding to the saddle point and say the value of, or write down the value of the game, or find out the value of the game. But here in this case saddle point does not exist, hence maximin is not equal to since maximin is not equal to minimax, saddle point does not exist here in this case. So this is a typical mixed strategy problem. Now this particular problem can be categorized as a mixed strategy problem. Okay. How do we proceed now? Now we will apply some probabilities here, because saddle point does not exist, so we have to apply mixed strategies. The first thing you have to do here is make two more columns. After B1 and B2, make two more columns, and similarly below the rows of A1 and A2, two more rows. So two additional rows and two additional columns you add in the payoff matrix now. Correct? And this P1 here will be the probability of A selecting A1, and probability P2 will be the probability of player A selecting strategy A2. So P1 is the probability of A1, P2 is the probability of A2. Similarly, Q1 is the probability of B1 and Q2 is the probability of B2. So whenever you represent P1 and P2, P1 represents the probability of A selecting, or A selecting A1, similarly, or which we call it as A exercising that particular strategy, that is A1, or putting forward that particular strategy. Similarly, P2 is the probability of A2, strategy A2. A1, A2 are the strategies of player A. Similarly, Q1 is the probability of B selecting B1, Q2 is the probability of player B exercising or selecting, player B selecting B2. Now what are these oddments? Oddments of A and oddments of B. If you look at it very carefully here, the oddments of A here will be the difference of the elements in the second row. So the oddments of the first row will always be the difference of the elements of the second row. So here the oddments of A will be 6 minus 2, the difference. Write the larger number first, then the smaller number, difference. 6 minus 2, that is 4. Similarly, the oddment of A2 or second row, that is this particular row, will be the difference between the elements in the first row. So that will be 7 minus 1. Bigger number minus the smaller number. So 7 minus 1 is 6. Now if you get, for example, now if when you actually subtract, this oddment should always be this particular value of 4 and 6. They should be positive always. Even if the difference, suppose you say 1 minus 7, we get minus 6 here, right? You take down the positive value. That's why I said always higher number minus the lower number. So the oddment of A1 will be, oddment of A1 will be the difference between the elements of A2. So higher number is 6, 6 minus 2, that is 4. This 6 minus 2, 4, we write here as oddments, and this 7 minus 1 will come here, that is 6. So these are the oddments of A1 and A2. Similarly, the oddment of B, when I find out the oddment of B, the oddment of B1 will be 7 minus 6, rather, 7 minus 2 rather, difference of elements in column 2. So the oddments of column 1 will be the difference of the elements in column 2. So it will be 7 minus 2, that is 5. This 7 minus 2. So that will be the oddment of this, and 6 minus 1, that is 5. That will be the augment of V2. That will be the augment of V2. So this is how you find out the augments. So hope there is be very clear about it. The augments of the first row will be the difference of the elements in the second row. The augments of the second row will be the difference of elements in the first row. Similarly, the augments of the elements in the first column will be the difference of the elements in column 2. Similarly, the augments of column 2 will be the difference of the elements in column 1. So that you have to. Now you have to find out P1 and P2. Now you have to find out P1 and P2. P1 will be equal to this augment of A, or the augment of A1, that is 4 divided by this 4 plus this 6. Total is 10, right? 4 plus 6 is 10. So P1 will be 4 by 10. Similarly, P2 will be this 6, this particular 6 divided by this 4 plus 6, that is 10. 4 plus. So that will be 4 by 10, and this P2 will be 6 by 10. Similarly, Q1 here will be this 5 plus 5 divided by 5 plus 5, that is 10, 5 by 10. And similarly, Q2 will also be equal to this 5 divided by 5 plus 5 is 10. 5 plus 5 is 10. So your P1 will be equal to 4 by 10, that is 0.4. P2 will be equal to 6 by 10, that is 0.6. Similarly, Q1 will be equal to 5 by 10, that is 0.5. Q2 will be equal to 0.5. Correct? So this is how you find out the probability values and the augment values in a mixed strategy 2 into 2 problem. Let P1 and P2 be the probabilities with which player A uses strategies A1 and A2 respectively. A's augments for the first row will be the difference of two elements of row 2 ignoring the sign. That is, if the difference comes as a negative number, suppose you have done 2 minus 6, you will get minus 4. What it says is ignore that negative sign. That's why it's always better to take the first highest greater element first and then lower element next. So difference between the first element and the second element. So if you take higher element minus lower element, you will get a positive value only. Correct? 6 minus 2 is 4. Similarly here, A's augments for the second row will be the difference of two elements of first row, row 1, ignoring the sign. So 7 minus 1 is 6. To find P1 and P2, that is probabilities P1 and P2, P1 is equal to this 4 divided by 4 plus 6, 4 divided by 4 plus 6, that is 4 by 10, that is 0.4. Similarly, P2 will be 6 divided by this 4 plus 6, 6 divided by 10, that is 0.6. The probability P1, that is the probability of player A using strategy A1 is 0.4 here, and the probability that player A will use strategy A2 is 0.6. So P1 is 0.4, P2 is equal to 0.6. P1 plus P2 is equal to 1. Similarly, let Q1 and Q2 be the probabilities with which player B uses strategies B1 and B2 respectively. B's augments will be the first column is the difference of the two elements of column 2, ignoring the sign. Similarly, B's augments of the second column will be the difference of two elements in column 1, ignoring the sign. Similarly, you find out Q1 and Q2. This 5 divided by 5 plus 5, that will be 5 by 10, that is 0.5. Similarly, Q2, probability of B2 will be this 5 divided by 5 plus 5, that is 5 by 10 is 0.5. Again, Q1 plus Q2 is equal to 1. So this means player B will use strategy B1 50% of the time and player B will use B2 another 50% of the time. The probability of B1 using B1 is 0.5. The probability of player B using B2 is 0.5 or 50%. So this is our mixed strategy problem. Basically, in a mixed strategy problem, you have to find out the probabilities associated with the players' strategies. So here it's a 2 into 2 game. So there will be, in a 2 into 2 game, there will be, if it is a mixed strategy problem without saddle point, then you will have a P1 value, a P2 value, similarly a Q1 and a Q2 value, and then you have a value of the game. So this is your table. You have to also find out the value of the game now. When the value of the game is given by this, what you will do, suppose this is A11, I will say this is A11, this is A12, this is A12, and this is say A21. Suppose this is A21 and this is A22. A22. This means first row, first column, first row, second column, second row, first column, second row, second column. Right? So this is the expression. So value of the game V, game V will be given by this into this. So A11, that is A11 into A11 into, I will say into A22 minus this value A12 into A21 divided by A11, the same terms here which you have used here, but the sum of that A11 plus A22, A11 plus A22 minus same one which is written above A12 plus A21. So this is the expression for a value of the game. So what you are trying to do here is 1 into 2 minus 6 into 7. So 1 into 2, that is A11. So here A11 is 1, A12 is 7, A21 is 6 and A22 is 2. Substitute these values in this particular expression. A11 into A22. So that is 1 into 2 minus A12 into A21, that is 7 into 6 divided by 1 plus 2, that is A11 plus A22, that is 1 plus 2 minus A12, that is 7 plus A21, that is 6. So you will get a value of the game. When you substitute all this, you will get a value of 4. You can see here 1 into 2 is 2, 2 minus 42 is minus 40. Here negative signs have to be taken into account. Don't ignore the negative signs because you are finding out the value of the game. You are finding out the net, you are taking into evaluation the gains and the losses here both. Correct? So plus and minus both should be taken into account here. So here the total here will be, value of the game will be minus 40 divided by minus 10. The numerator here will be 1 into 2 minus 42, that is minus 40, and the denominator will be 2 plus 1 is 3, 3 minus 2 plus 1 is 3, 3 minus 13, that is minus 10. So minus 40 minus 10, which is equal to 4. So your value of the game will come to 4, a value of 4. So it is a positive value here. So value of the game is a positive value, but unlike your pure strategy problem, you cannot here say that a particular player will be the winner, because it's probability based. It's probability based mixed strategy problem. So you can only say that since the value of the game is positive here, we can say the game is loaded in favor of player A. The game is loaded or inclined or favored towards A, inclined towards player A, because it's a positive value of the game. So you can write down here, you just look at this. The probabilities with which player A will use the optimal strategies are 0.4 and 0.6 for the strategies A1 and A2 respectively. Similarly, the probabilities with which player B uses optimal strategies are 0.5 and 0.5 for strategies B1 and B2 respectively. And the value of the game is equal to 4. And the value of the game is equal to 4. This is a mixed strategy problem which is solved by analytical or arithmetic method. Let us take another problem now, where again two players are involved, player A and player B. They have strategies of B1 and B2, and the payoffs are given in the payoff matrix. Solve the above game using analytical method. Again, row minima, row maxima we find out, and then find out the maximin and the minimax values. Maximin is not equal to minimax, hence saddle point does not exist. So again, it's a mixed strategy problem. So we will proceed as we have done in the previous problem, example in the same session. Just we have concluded, we have finished one completed one problem. Just like that, since we have established here that maximin is not equal to minimax, saddle point does not exist. So we move to the next step now. We again find out the P1 and P2 values, and then first find the oddments, then from the oddments you will find out the P1 and P2 values. The elements were 4, 0, 0, 8. Now find out the oddments. Oddments for A will be the difference of the elements of the second row, so 8 minus 0, that is written here. The oddments for A2 will be the difference of the elements in first row, so 4 minus 0, 4. Similarly, the oddments for column B1 will be the difference between the elements in B2, 8 minus 0, 8. Similarly, the oddments for B2 will be the difference of elements in B1, 4 minus 0. Correct? Okay. So now we will find out P1 and P2. So P1 will be this 8, this particular value 8, 8 divided by 8 by 8 plus 4, that is 12. That will be 8 by 12. And similarly, P2, this 4 divided by 8 plus 4, that is 12. So P1 will be 8 by 12, P2 will be 4 by 12. Similarly here, Q1 will be this 8 divided by 8 plus 4, that is again 8 by 12. Q1 will be 8 by 12, 8 by 12, and Q2 will be 4 by 12. Q1 plus Q2 should be equal to 1. Similarly, P1 plus P2 should be equal to 1. Similar to the previous problem that we have discussed in the same session, similarly we solve this particular problem also. So in any problem, first find out whether there is a saddle point. If there is a saddle point, no need of doing all this analytical method. Directly wherever that maximin is equal to minimax value, that will be that particular point will be the saddle point, and the value of the game will be that particular value at that intersection point, and the optimal strategies directly you can find out. There will be, these optimal strategies will be 100%, not, there will be no probability, 100%. If there is a pure strategy, whatever strategy he chooses, A and B will be 100%, 100%, okay, 100% in both cases. 100 in the sense, P1, there is no P1, P2 there, full probability, because it's definitely going to take that, because there is a saddle point there, saddle point, okay. Let P1 and P2 be the probabilities with which player A uses strategy A1 and A2 respectively. Similarly, you find out the oddments for player A. The oddment for the first row will be difference of two elements of row 2 ignoring the sign, which is equal to 8. Similarly, the oddment for the second row will be the difference of the two elements of row 1 ignoring the sign. Finding out P1 and P2, similarly we get P1 is equal to 8 divided by 8 by 4, that is 8 by 12, that comes to around 0.67 if you convert it into decimals, rounded off 0.67. P2 will be equal to 4 by 12, that is 1 by 3, that is 0.33, and P1 plus P2 you know is equal to 1. So this is exactly similar to how we have done for the previous problem. In the same session we have discussed a previous problem. Same way you find out for both the strategies, that is for both the strategies of both the players, that is P1 P2 for A, Q1 Q2 for player B. Let Q1 and Q2 be the probabilities with which player B uses strategies B1 and B2 respectively. So the B's oddment for the first column will be the difference of two elements of column 2 ignoring the sign. So it will be 8 minus 0 is 8. Similarly, B's oddments for the second column will be the difference of the two elements of column 1 ignoring the sign, that is 4 minus 0 is equal to 4. Similarly, Q1 will be this 8 divided by 8 plus 4, this 8 divided by 8 plus 4, 8 by 12, that is 0.67. Q2 will be this 4 divided by 8 plus 4, that 4 by 12, which is equal to 0.33. Q1 plus Q2 is equal to 1. If I find out the value of the game now, 4 into 0, this 4 into 8, 4 into 8 minus 0 into 0, 4 into 8, 4 into 8 minus 0 into 0, you can see here 4 into 8 minus 0 into 0 divided by 4 plus 8 minus 0 into 0. So we get the value of the game as 2.67. When you substitute, and you will get a value of 2.67, which will be the value of the game. Same, if you consider this as A11, consider this as A11, consider this as A12, A12, so consider this as A1, A21, A21, and this is A22, and apply the formula, same formula. 4 into 8 minus 0 into 0 divided by 4 plus 8 minus 0 plus 0. So that will give you 2.67. So the probabilities with which player A uses the optimal strategies are 0.67 and 0.33 for strategies A1 and A2 respectively. The probabilities with which player B uses the optimal strategies are 0.67 and 0.33 for strategies B1 and B2 respectively. And the value of the game is equal to 2.67. So again it's a positive value. So since it is a positive value, the game is loaded in favor of player A. Now continuing with the 2 into 2 games without saddle point using arithmetic or analytical method, let us take another problem here. Of a coin, we are talking about a true coin now, a coin which is having a head and a tail. So in a game of matching coins with two players, player A and player B, there are two players, player A and player B. Each one is having a true coin in his hand, and both of them are going to flip the coin simultaneously. Both of them, player A has a true coin, player B also has a true coin with him, and both of them simultaneously flip the coin at the same time. Whatever coins they have in their hand, they will flip it together simultaneously at the same point of time, and the result, and what are the different results or the payoffs for each situation or each there is a particular way in which these two coins will fall down, right? What are the possibilities? Just let us go through this problem. So in a game of matching coins with two players, player A will win or wins 1 unit of value when there are two heads, wins nothing when there are two tails, and loses half unit of value when there is one head and one tail. Solve the above game using analytical method or arithmetic method. Also determine the payoff matrix and the best strategies for each player and the value of the game. So there are two players, two coins. Each player has one true coin with him. Both of them flip the coin simultaneously, and if the coins fall as two heads, both the coins fall as heads, that is, the coin that A has tossed falls head, and similarly the coin that player B has tossed also falls head at the same time. There will be two heads. So in that case, player A will win 1 unit of value. This 1 unit could be, say, some incentive or some monetary value. Let us say 1 rupee. 1 rupee or 1 unit of monetary value, or 1 unit of value. Player A wins 1 unit of value when there are two heads, wins nothing when there are two tails. If both the coins fall as tails, A tosses, it falls tail. Similarly, same point of time, B also tosses and it falls tails. So there are two tails now. A will win nothing. A will win nothing. A wins 0. That is, he neither gains nor loses anything. And A loses half unit of value when there is one head and one tail. And A will lose half unit of value when there is one head and one tail. So if there is one head and one tail, A will lose half unit of value. That is, there are two possibilities here. Player A's coin can fall as head and player B's coin can fall as tails. So then it becomes one head, one tail. Or player A's coin can fall as tail and player B's coin can fall as head. Even then it is one head, one tail. So please be very clear here. If there are two heads, player A wins 1 unit of value. If there are two tails, player A does not win anything. Player A loses half unit of value when there is one head and one tail. So you have to first determine the payoff matrix. So here the payoff matrix is not given, unlike some of the problems that you have solved earlier. So reading the situation here, understanding the situation, you have to now construct a payoff matrix or a payoff table and then apply the analytical method and find out the best strategies for each player and also find the value of the game. So what will be the payoff matrix? Payoff matrix. Your payoff matrix will look like this. Your payoff matrix will look like this. You can see here A1, that is player A, if his or her coin fall as head and B's coin also falls as head, then there will be two heads. A wins 1 unit. Similarly, if A's coin falls as head and B's coin falls as tail, then there will be one head and one tail. A loses half unit, that is minus 0.5, because he loses half unit. Similarly, if A's coin falls as tails and B's coin falls as head, then again there is one tail and one head, so A will lose half unit of value. And similarly, if A's coin falls as tail and B's also falls as tail, then there will be two tails and hence A will neither gains anything or nor lose anything. So that's why we put 0 here. When he wins 1 unit, payoff is 1 for A. Similarly, when he doesn't win anything nor lose anything, the payoff is 0. When A loses half unit, it is minus 0.5. So two heads, A wins by 1. Two tails, 0, that is neither win nor loss, or neither gain nor loss, When one head, one tail, you can see a combination of tail and head here. One tail, A's tail and B's head. A's coin has landed up as tail, B's coin has landed up as head. A loss of minus 5, minus 0.5. A loss of minus 0.5, or a loss of half unit. A loss of 0.5, that is minus 0.5. 0.5 loss to A. Similarly here also, one head, one tail. So a loss of half unit. So minus 0.5 here indicates a loss of half unit. So this is the payoff matrix which you have to construct. That is what you have to construct, and then as we have done in the previous problems, we will first find out whether there is a saddle point for this problem or not. Can it be considered as a pure strategy, and can we find out a optimal strategy with saddle point? Let us check. You can see here the row minima and the column maxima are given. The maximum value is not equal to the minimax value. Here you can see here this minus 0.5, there are two same values, so the maximum will be minus 0.5, and here the minimax will be 0, minimum of the maximum, that is 0. These two are not equal, so maximum value is not equal to the minimax value, so saddle point does not exist. So here the oddments of A1 will be the difference of the elements in the second row, so that will be 0 minus 0.5, that is 0 minus 0.5, that will be 0.5 plus 0.5, because the oddment of A1 will be the difference of the elements in the second row. So 0 minus 0.5, that is equal to plus 0.5. Similarly, the oddments of A2 will be 1 minus 0.5, that will be 1 plus 0.5, that is plus 1.5, 0.5 and 1.5. Similarly here the oddments of B1 will be 0 minus 0.5, that will be 0.5, and similarly the oddments of B1 will be, or B2 will be, oddments of B2 will be 1 minus 0.5, that is 1.5. So these will be the oddments. Oddments of A1 will be 0.5, oddment of A2 will be 1.5, similarly oddment of B1 will be 0.5, and oddment of B2 will be 1.5. So ignoring the signs was only for this final value, the difference value. Here you cannot ignore these signs because they indicate the losses that indicate this minus and plus are very significant here when you find out the oddments here. So these signs will be taken into account. Only this. That's why the higher element, 1 is higher element, 1 minus 0.5, that will be the oddment of A2. Similarly 0 minus 0.5, that will be plus 0.5, that will be the oddment of A1. So similarly for B1 and B2. Let P1 and P2 be the probabilities with which player A uses strategies A1 and A2 respectively. So the A's oddments here is 0.5. Similarly for A1, A1's oddment is 0.5, A2's oddment is 1.5. So P1 and P2, P1 will be 0.5 divided by 0.5 plus 1.5, that is 0.5 by 2, that is 0.25. Similarly here P2 will be 1.5 divided by 2, that is 0.75. P1 plus P2 is 1, which means player A will use strategy A1 25% of the time and player A will use strategy A2 75% of the time. Let Q1 and Q2 be the probabilities with which player B uses strategy B1 and B2 respectively. So the B's oddments, similarly you find out it will be the difference of the two elements of column 2 ignoring the sign, 0 minus 0.5, that is 0.5. Difference of the two elements of column 1 ignoring sign, so 1 minus 0.5, that is 1.5. To find Q1 and Q2, again 0.5 divided by 0.5 divided by 0.5 plus 1.5, that is again 0.25 and 0.75. You get 0.25 and 0.75 here. So Q1 plus Q2 is equal to 1, which means the probability that player B will use strategy B1 is 25% and the probability that player B will use strategy B2 will be 75%. Q1 plus Q2 will be equal to 1. Similarly, you find out the value of the game here. Value of the game will be 1 into 0. You can see here 1 into 0 minus 0.5 into minus 0.5. These signs have to be taken into account here. Don't ignore these individual signs of the payoff values. They are very important. 1 into 0 minus 0.5 into minus 0.5 divided by 1 plus 0 minus 0.5 plus minus 0.5, which is equal to minus 0.25 divided by 2, which is equal to minus 0.125. So value of the game is minus 0.25 divided by 2, which is equal to minus 0.125. So here the value of the game comes as negative, which means the game is slightly loaded in favor of player B, not player A. The previous two problems in mixed strategy, you got value of the game positive, which means the game was loaded slightly in favor of, or loaded in favor of player A, because value of the game was positive in the previous problems. Here the value of the game is minus 0.125, a negative value. So the game is inclined, or game is loaded in favor of player B. The game is loaded in favor of player B here, because value of the game is negative. So the probabilities with which player A will use optimal strategies are 0.25 and 0.75 for strategies A1 and A2. Player A will use strategy A1 25% of the time. Player A will use strategy A2 75% of the time. Similarly, player B will use strategy B1 25% of the time. Player B will use strategy B2 75% of the time. And the value of the game is equal to minus 0.125, and the game is loaded slightly in favor of player B. So this is about how you solve a mixed strategy problem, or we have seen how to find out the odd bends of each strategy, find out the probability values associated with each strategy, then value of the game using the arithmetic formula. That is why it is called as an analytical or an arithmetic method. So in the next session, we will discuss about dominance rule. That is, what happens if a problem is not 2 into 2? Higher order matrix, a higher order payoff matrix, say three strategies of A, 3 strategies of B. If such a problem exists, can we apply this particular analytical formula here of value of the game, etc.? No, this is applicable only to 2 into 2, correct? 2 into 2 problems. So can we reduce a higher order matrix problem, say a 3 into 3 or more than 2, say this is 2 into 2, something like say a 3 into 3 or a 4 into 4 or a 5 into 5 matrix problem. A has 5 strategies, B has 5 strategies. Okay, can such problems be reduced to a 2 into 2 matrix, so that this analytical method can be, or arithmetic method can be applied to it? So in the next session, we will be discussing about dominance rule, or the principles of dominance in game theory. Thank you, students.